Good afternoon, everyone, and welcome to the next edition of WTA's webinars. This is Alan Phillips speaking. I'll be doing the webinar of today. Thank you very much for joining us. We'll be starting in a few minutes, right at 3 o'clock. Just a few housekeeping notes. You're all on mute to start with. There is a question area to enter questions throughout the course of the webinar, and I will try to answer those as I go along, as well as when at the end when we take some time for questions and answers. I'd like to thank the WTA for setting up these events, and especially to thank Kelly Worthington for taking the time to do this for us. I believe that she's unavailable to attend today, right? But we'll keep marching on without her. Good afternoon. We'll start up right now. My name is Alan Phillips. I'm from Tejas Networks. I am Group Director for Channel Strategy and Solutions. And today we will take the opportunity to discuss rural network modernization and for both packet and optical transport networks. We're going to concentrate primarily around 6 technologies that improve rural transport networks. These 6 technologies didn't really exist very well until recently. And they've come up through, been developed for the communications industry from the long haul networks, from larger metro networks, but they're becoming more and more applicable to the rural telecommunications networks. And they provide a few things that were never possible before. They provide better economics, much higher bit rates at much lower prices, better service control, and all the functions that you need to have to modernize from a traditional transport network, collect that and move it forward to a transport network that will last you the next 8, 10, 15 years from a technology perspective. These 6 technologies I'm going to talk about today is 6 technologies I'm going to talk about today are network scale circuit emulation, being able to circuit emulate TDM services over a packet infrastructure at a network level, right? Go beyond that provisioning of services, TDM services from a point-to-point, small cell DS1s, etc. Improve passive optics, more efficient packet technologies, better services control, the advancement in 100 gig optics, especially associated with DWDM optics, and FPGAs, field programmable gate arrays. These field programmable gate arrays allow hardware to be redefined and increase functionality over the life of the product. And this flexibility in the hardware goes beyond what software can offer and allows you to reprogram what the hardware can do. These technologies are available within the industry, and I'll view them from an industry perspective on how they will help modernize your networks. For example, network scale circuit emulation can dramatically increase the return on investment for network evolution. you can combine multiple technologies onto a single packet infrastructure and collapse 3, 4, 5 different types of infrastructure onto one infrastructure. Improved passive optics, right, will drive lower fiber usage and lower costs within the networks. More efficient packet technologies provide for faster protection and fault isolation. Better services control can provide lower operations costs and lower training costs. And services control goes beyond just, how to manage the box, but how a user interfaces to that box and how a user interfaces to the network. And this will allow companies to explore new and faster provisioning models, new services to customers at a lower training expense to their operations teams. 100 gig optics provide rapid deployment of with alien wave technologies and the lowering of DWDM, right, as you move to 100 gig. And FPGAs provide more applications from each module than we've ever been able to do before as an industry. So we'll start off with a few of those right away. The first one is looking at DWDM for rural network modernization. Long-haul networks paved the way. Now it's time for them to share the benefits. All the work that they've done on the long-haul networks and all the technologies they've created for the long-haul networks, we can move into the rural networks. Maybe not all at once, but we can pick and choose which technologies makes the most sense as we move those into the rural networks. Right? First one of those is an easy way to increase fiber network utilization, right? With or without moving to a full DWDM solution. So how can I get a little bit of DWDM going, get a little bit of optimization going without having to go to a full DWDM solution? To look at that, we're going to have to look at optimizing fiber usage. Currently, right, we can look at the left-hand side of this slide and say, our fiber usage is kind of like a divided highway. It's unidirectional for both, DWDM or CWDM, right? It uses two fibers going one way, or a fiber going one way and a fiber going the other way, right? And this is pretty good in a lot of respects. It can support many wavelengths, can support a lot of distance to it, right, with DWDM. But CWDM is kind of short range. It really doesn't work very well for longer distances. There's no amplifiers for it. Forward error correction's never really been built for it. And the cost price of CWDM optics is not that much lower than DWDM optics these days. The other option is to look at BIDI. Now that bidirectional optic will allow you to send two wavelengths of light down the same fiber, one wavelength, one on the other wavelength, just like a typical rural road. You get one service on a pair of fiber, or on a single fiber, I should say, but your distance is limited, and it's severely limited, and there's no amplification possibilities for that. Right? But there's an option for a lower cost, and that is to take a single fiber, right, and divide it into 2 or 4 lanes, right, with greater distance than BIDI optics, and have something that runs on DWDM so I can reconfigure it later to a full DWDM system without having to throw away any optics or any investment that I put into the network, and create a solution that says, I can make that longer distance. I can use a single fiber. I can really optimize my fiber and get, 20 gigabits of traffic or 40 gigabits of traffic onto a single fiber. And this is done with something that's been used for a very long time in longer distance networks or in microwaves with forward error correction. Right? Now, there's a lot of different forward error corrections, and there's some that are really good that for long distance networks, and these are these long curves here, hard decision FEC for 100 gig or a soft decision FEC for 100 gig. And these are really good for 100 gig networks. They really extend out how far a wavelength can go before it has to be amplified. And it really improves the quality of 100 gig signals. Right. There are other forward error correction signals that are traditional for 10 gigabits. Now there's one here that gives you about 6 dB of gain, and it's a pretty standard one. It's called, it's called standard FEC, right? But 6 dB of gain is pretty darn good, right? And that's a lot of distance. And there's some slightly more enhanced FECs and different numbers and different naming conventions for them all, but they get a little bit more expensive and they take a little bit more processing power and they get a little bit more difficult to deploy as you start to run up from the 6 dB gain right up through the 8 and 9 dB gains, right? All of that's very valuable if you're trying to get that long distance, but it's really difficult to see the economic benefit of going that much heavier in the processing in a rural network, right? And the more coding gain you give it, the longer the network delay is, because you add more overhead to it and more processing power to it. So what the industry is providing for rural telecom networks is the ability to put together a solution that uses, standard XFPs or SFPs, right? And a standard packet switch or sonnet switch or anything like that, and be able to combine multiple wavelengths, right? Either that be, a left to right wavelength or a right to left wavelength, or two of those onto a single fiber, right? And these are very cost effective. So we're combining together a few things. We're combining together OADMs from a DWDM network. We're combining together standard XFPs that exist in the network, in the industry, fairly standard packet switches, and forward error correction that's from the long haul industry, and pulling all those together, putting it onto a single fiber, and we're able to double the distance of a BIDI optic, right? And not for double the price. So this is what the industry is capable of doing for you, and saying, listen, we want to do a rapid deployment here. I've limited on fiber. I want to be able to get 10 gig from point A to point B. I want to use as few fiber as possible. How do I get that done? And you could do that up to 90 kilometers with standard optics, a little bit of forward correction, and a passive optical mux to put those two wavelengths, one going east and one going west, onto the same fiber. For the, if you want to get double that capacity, you have to get a little bit more channels in there and you have to do a little bit of extra work, but it doesn't shorten your distance very much. The distance goes from 91 kilometers down to 86 kilometers. And if we would do 4 by 10 gig E, it drops to about 70 kilometers. And this is all, standard XFPs, SFP pluses distance, standard forward error correction, and standard off-the-shelf OADM capabilities. Most BIDI optics have a limit of 40 kilometers. So we're getting, double the distance to 1.5 times the distance, right, for a very similar price. But there's no amplifiers involved, and there's no need to go out there and learn how to do DWDM extensively. This is just plug and play. Another thing that's happening that we're able to do now because of all the work that's being done in the long haul and the metro markets, what we can do for the rural environments is start to bring 100 gig DWDM into play. Right? And whether that be one wavelength to start with, right, or multiple wavelengths, you know, customers can look at it and say, is it really viable for me? The economics have changed rapidly over the last few years. Right? In 2014, we were seeing, you know, roughly the same number of 10 gig optics being sold as 100 gig optics. And this is the number of ports around the world. And by 2016, we were seeing a little bit of an increase in 10 gig optics and 3 times the amount of 100 gig optics. Right? In terms of capacity. And 2018, we expect that to double again. So while 10 gig isn't going away from a capacity perspective, what is happening is the industry is deploying so much 100 gig that the prices are dropping significantly. Right now, we're seeing more 100 gig and 200 gig deployed, almost double the amount of 100 gig and 200 gig versus every other WDM type, whether that's 10 gig or 40 gig. And that margin will continue to widen. So pluggable 100 gig DWDM optics are extremely cost competitive, and the price continues to drop almost every year. Right? We're seeing technology improvements. We've seen them last year in 2017, right? And this year, if things stay on track, this chart will change again because prices, there's a new technology coming out that will move them down even faster. Right? And where is that coming from? Well, for coherent optics, that's coming from a couple of things. Right? And I'm giving you a picture from one of the world's leaders, Acacia Optics. They have a program. They're one of the world's largest deployers of 100 gig pluggable optics. And they take their transistors, which, you know, they're digital signal processors for coherent, which are about the size of a quarter, right? And they put them next to a photonic integrated circuit, which is a laser on a chip, which is about the size of a dime, put those together onto a single board that is put into a pluggable. And they do that, and they've been shrinking the size of that package down from about the size of, I don't know, right? The first ones were size of an Apple iPhone 10, the large screen one. And now the same amount of bandwidth, actually it's double the amount of bandwidth, I should say, is about the size of an Apple iPhone small screen. And the next generation will go to half that size. So improvements, rapid improvements in that area, both in the size of the DSP and the size of the silicon-based lasers, have led to being a situation where the price of 100 gig optics versus 10 gig optics is dropping rapidly. Right? So this was the price of 100 gig optics versus a 10 gig optic in 2011. Right? And they're both pluggables, they're both DWDM optics, they both have the same range, right? The same capabilities. Of course, the 100 gig optics will give you more bandwidth, but you know, just from a price perspective, per optic, right? And if we said, okay, we're going to put 10 of those 10 gig optics together, right, to do 100 gig of bandwidth. That's the orange line. And we're going to put 100 gig optic out there. What's the price comparison look like? Well, in 2011, 100 gig was about twice the price of 10 gig, right, for DWDM. And by 2016, it had reached a crossover point where 100 gig was cheaper than 10 by 10 gig. And the 10 by 10 gig market has kind of flattened out in price. It might see some continued downward movement, but it's pretty much flattened out on price, right? But the 100 gig market continues to slide down very quickly. And the projection now is that in 2018, the price of a 100 gig optic will be about 70% of the price of 10 gig optics. And 100 gig optics are much easier to deploy. It's much easier to manage a single 100 gig wavelength than it is 10 gig wavelengths. Right? Much faster, much easier bandwidth to control, and coherent optics are inherently easier to use than the standard direct detection 10 gig optics when it comes to doing DWDM. And I might be a little bit conservative on that 2018 number for 100 gig, because there's a new technology coming out that isn't coherent, that will work for smaller networks in the 300, 400 kilometer range, that will probably be down even 20% less than that blue line that I'm showing. And that gives us the opportunity for new network deployments. Instead of looking at a long haul network only for 100 gig, which is basically what 2015 was. There was some metro, but it was mainly long haul. And 2016 through 2018, almost everybody's been growing out to following the curve of deploying out 100 gig in the metro regional market. Right? We're starting to see a lot more interest in doing 100 gig in the rural and aggregation market. And whether it's not, it's coherent DWDM or saying I want to skip DWDM altogether and use longer reach 100 gig optics, which can currently cover about 40 kilometers without non-DWDM, 40 kilometers. 100 gig is making a lot more financial sense and a lot easier operational sense than 10 gig for the core of networks. It's still not going, 10 gig is still going to have to be there for the aggregation space and out to the edge of the network. And that leads us to the ability to look at 100 gig as an alternative to a 10 gig DWDM network in the core. On the left-hand side, I have a drawing of all the elements that would go into a 4-node DWDM network, right, with add drop capabilities from anywheres to anywheres. Well, with 100 gig, you can remove all of the dispersion compensation modules, a lot of the planning around dispersion compensation, in fact, almost all of it. Remove many of the optical add drop muxes, most of the amplifiers, right? You reduce the amount of pass-through, which is a wavelength passing through a node without dropping any traffic, and that makes it operationally much simpler to use. You cut the number of cards in half, and you can easily double the capacity of the 10 gig network, right, by going to a 100 gig system, right? It's simpler to diagram, simpler to deploy, and if it's simpler to do those two things, it's simpler to understand and to operate. Right? So 100 gig has the advantages, and it's going to continue to grow those advantages in the core of the network. Right? The optics are getting cheaper, pluggable optics continue to move along. Right? For those of you who are considering saying, you know, I've got this great 10 gig network in place, could I just add 100 gig to it? Well, yes. The nice thing about 100 gig coherent optics are they're really easy to add to a 10 gig DWDM network. Coherent optics are a lot more flexible than 10 gig direct detect optics. So if you take a network that is tuned to do 10 gig DWDM and you don't want to touch it, you don't want to leave it, you know, move it around and anything, but you say, hey, can I use that asset to get more 100 gig capable, you know, 100 gig capability out of it? You can put 100 gig onto that in a point-to-point manner or a ring manner, just depending on your network, right? And deploy it quickly. Now, we've done this within Tejas, but you know, other companies have done it as well, and that's because 100 gig works and deploys so much easier than 10 gig. So if you got a network that's at 10 gig and working as 10 gig, you can reuse the same amplifiers, you can reuse the same dispersion compensation, and you just add 100 gig to it, right? And you just add 100 gig as cost effectively as possible. Now, these three things that I've talked about from the DWDM perspective allow you to, you know, increase the bandwidth at the edge of your network to 10 gig and 20 and 30 and 40 gig as quickly as possible by using single fibers to be able to do that without having to lay new fiber out to into the access region. It allows you to upgrade the core, right? If you need a new core network, and cost effectively go to 100 gig, or in this case, add in 100 gig to an existing 10 gig network without doing a lot of changes and get a, you know, increase your capacity. And that will set up the core of your network, the optical layer of your network, ready for those additional services that are coming along, like higher broadband rates, right? 5G, more extensive 4G, right? Higher bit rates 4G, right? Internet of Things, all of that is going to add traffic to your network. And how you can manage that in the core of your network is going to become important. So there's cost-effective ways of doing that. And we'll start to get into some of those as we go through the next portion of this presentation. The first thing that I'm going to talk about is programmable hardware. Sometimes it's just not enough to have network processor units that can change their software and fixed silicon deployed in your network, right? You might get some flexibility out of it, but services are changing so fast and requirements are changing so quickly that it's difficult to keep up with the demands unless you have some level of flexibility in the hardware itself. Right? And there's a few things that, you know, we all know that are going to happen here, right? Optical ports are going to continue to exist. And those optical ports are going to be, you know, sometimes they're going to be SONET, but most of the time they're going to be Ethernet. Well, the great thing is hardware is out there that will handle a single port, would be able to handle optical, you know, OC3, 12, 48, 192, as well as GigE and 10 GigE. So you don't have to change the optical port. You might have to change how the hardware views that port and how the software operates that port, but you don't have to change the port. The other part of it is you can look at this and say, how can I, you know, do things that change the way I operate my network? How can I get those old services that I still need to have around onto a new packet infrastructure cost effectively? Because it's difficult to say, I'm going to, you know, take this aging SONET ring and replace it with another SONET ring. You might be able to do that, might be cost effective for you. Sometimes those SONET infrastructures are so small, you're kind of sitting there going, well, do I really want to deploy a SONET ring for a few nodes? And the flexibility of an FPGA to provide that capability to do SONET one day and packet the next day is very, very, very valuable when you want the asset to last as many years as possible. So what is an FPGA? Well, an FPGA is a field programmable gate array. And a field programmable gate array is a piece of silicon that allows you to change the instructions of that silicon, not program it like a PC, but actually change how the hardware operates. You can download it and say, I want you to do Ethernet today or SONET today and the Ethernet tomorrow. And the great thing is about that is it always runs at wire speed. So when you change it from one to the other, the electrons still flow through it, as fast as they can. You're changing how the gating works so that it looks at the bits differently. Instead of looking at them as SONET bits, it looks at them as Ethernet bits. But effectively, it's running at wire speed. You're not running that software that can only handle so many, megabits per second. You're looking at hardware that can run at gigabits per second. And up until recently, we haven't had the density on an FPGA to be able to do some of these things. But the great technology in the world has allowed us to go on this graph, has allowed us to take FPGAs that used to cost, let's say, for example, $10,000, right? And over the last, for X number of gates, pieces of logic, right? We've reduced that down to now costing $2 for X number of pieces of logic in the space of 25 years. So this is the power and the price. They just continue to drop. And I imagine they've dropped even farther since 2015. Right? While the capacity of a single FPGA used to do a few gates, have a few logic elements, now it's doing tens of thousands of pieces of logic. And for every logic element is one more instruction it can do and one more type of traffic that it can handle. And the denser it gets, the more powerful it gets, right? The better it is to be able to handle a growing, changing telecommunications network. So every year, and this is out of Asia Pacific, but it still applies globally, right? This is just the best representation I could get. Every year there's been an increase in the use of FPGAs around the world. And it's been a fairly steady one through last year, steady growth, but it's been picking up and will continue to pick up over the next few years. That's because of the flexibility. And the largest user of FPGAs by far has been telecom. And every year that growth is, the size of that orange candle has been growing, right, as fast or faster than any other portion of the candle. So telecom manufacturers and industry, the industry as a whole has realized the importance of FPGAs. Now, a lot of these FPGAs also are used in data processing. As you can see, this orange in data centers, right? And it's growing as well. It's also used a lot for Internet of Things, although they classify it as industrial or automotive, right? Those are the Internet of Things applications, right? And we'll probably see it segmented out again for Internet of Things over the next few years. But the FPGAs brought one thing specifically for the telecom market that we're in, which is the transport piece. Up until recently, it's been difficult to understand doing a SONET network element or a SONET network, right, and moving it to packet at scale. Like, I'm not talking about doing 16 DS1s. I'm talking about doing 50, 100, 150. I'm not talking about doing a few OC3s I'm talking about doing as many as you want to. And around about 2015, we finally hit the point where the FPGAs were large enough to make it cost effective to have 1 or 2 cards handle, like 2 cards in a protected mode, handle 5 gig of TDM traffic. Right? That's half of an OC192 MSVP at drop at every node. So you could do an OC192 rig over packet by having an FPGA take that TDM traffic in and convert it to packet and then run it over the packet ring. And this was a game changer. This allowed people to move and do an evolution. Right? We use it a lot in hardware in the telecom industry. Right? And I want to walk through some of those. For example, this one card can serve 3 purposes. It can serve a purpose of being a 100 gig interface to an OTN switch, or do 10 ports of 10 gig to an OTN switch. Right? By changing the FPGA configuration, it can now become a 5 ports of 10 gig to 5 ports of 10 gig for client to line if you wanted to do 10 gig in the access. Or, again, just reconfigure the FPGA, it can become 10 gigs mux bonded into a 100 gig line. Right? One card, right? Buy the optics you want, change the optics if your design changes, right? And you're able to move forward as your network changes and grows. And this is based upon the industry providing FPGA capabilities. Right? Another example is a card like this one that takes those 8 optical cages and says, what do I want to do with them today? You can do a circuit emulation app. You could use it as a SONET interface for just OC3, 12, 48. You could use it as an Ethernet trib for gig-E's, 10 gig-E's, 10 100 1000s. Or you can use it as a DWDM tributary app. You can plug and play with your applications. Right? And it doesn't require sending the card away. These are all reprogrammable. Right? And there are multiple vendors in the world that are using this technology to make hardware more flexible and available. So the network scale circuit emulation has allowed us to take SONET networks and meld them together with packet transport, right, within the industry, and move DS1s and OC3s and OC12s, whatever interface we want from the SONET world, right, take them over a packet transport and add in carrier Ethernet, 10 gig, 100 gig transport along with it, right, and create a new modernization platform. 7, 8 years ago, when people talked about modernizing networks, they talked about taking a TDM backbone and overlaying a packet infrastructure and leaving the TDM backbone alone, and eventually, maybe, if something worked out, right, the TDM would go away and everybody would just be riding packet going forward. Well, that hasn't happened. There's too many TDM-based services. There's too much TDM still left out there. And it's too much of an economic burden to wipe it all out in 1 single year, or even 5 single years. But the demand for new packet is still there. So by adding in a packet transport to handle that growth in packet services, and simply using a few cards to take the SONET with it, you can roll SONET onto a packet transport solution and create a converged packet transport solution, right? And this is a function of having FPGAs, right? It's a function of being able to say, I've got a packet switch that I've added in cards to do the TDM, and I have cards that do the packet, and we reprogram the FPGAs as we need to, as we go along, and all of a sudden you've got a packet infrastructure that you learn once that carries you forward for years, and a TDM that comes along with it. It can be used for simple things like DS1 circuit emulations for servers for PON, evolving it out so that you can like quickly move forward circuit emulation servers, high density servers, to do TDM services, right, off of OLTs, and let the OLTs do the high revenue broadband services that they really are built for, right, instead of occupying them with low density DS1 cards. And they can also work with solutions that say, hey, I want to replace an MSPP network and build a packet transport network at the same time and migrate out old MSPPs after you put in this upgraded packet transport solution, right? And FPGAs and the combination of packet is able to do all of that and still allow you to do all of the Ethernet services that you're used to at the top part of the screen, and all the TDM services that you need to migrate off over a longer period of time to experience that return on investment. So that there I've walked through, you know, the effect of DWDM and 100 gig. That was 2 of the aspects of the 6. Where FPGAs and what they're able to do for you, you know, rural telecom networks in terms of giving you hardware that is able to stay with you for many years, yet change the services it can provide, so it stays current for many longer years instead of just staying in the network providing old or less effective revenue. And now I'm going to start to talk about things that we bring to the other 3 things that are left. I'll start that by talking about the Internet of Things and rural network modernization. The Internet of Things brings the next wave of information control overload. The information that's in the Internet of Things is not very large on a per byte level, or a per application level, or a per device level. It's relatively small. But the problem is, it's not just a few things. It's everything gets tagged. It's animals get tagged so that your dairy industry that's in your area can say, okay, here's all my animals. I know where they're at. I know, you know, whether or not they need to be milked or they don't need to be milked, or, you know, whether they're being fed properly, whether they're hydrated properly. All of these are, you know, important things. A small device that provides this type of information can save the investment of a very expensive dairy cow, right? It's there for plants, right? Not every single plant, but within an area to make sure that, you know, the growth rates are right, that you're not experiencing insect overload, that your herbicide was effective, that you're sitting there with enough rain to be able to address the growth needs of the crop at the proper time, right? And all of these devices will grow, you know, be used more and more to allow these industries to become more and more effective, right? And that information will be exchanged every day, all day, right? So the estimated number of devices, right, will grow from an estimate of 30 million in 2015 devices to 75 million just for agriculture globally, right, in a 5-year span. That's millions of devices, 75. And the average amount of data generated by the average farm per day, right, will rise from almost nothing to within, the near future to, a gig a day. Right? Continuously streamed at any point in time. So from a telecom perspective, the connectivity is probably relatively simple. It's another broadband connectivity, right? It's the control aspect of it. It would be very difficult. Give you some examples. This was, brought to us by the COB project, right? They look at, remote sensing for mapping, monitoring climate conditions, investments in livestock, tractors, everything gets tagged. Now they have a reason that they want to tag everything because they want to sell this stuff. But I come from a farming background. If it makes money, people will use them, right? And whether it's remote monitoring, whether or not it's ensuring that the crops are growing fine, right? And who doesn't love a good drone mapping out your fields on a day-to-day basis? So all this generation of data will happen, right? Moisture content in silos, right? Got enough feed in the feeders, who's drinking lots of water, who's over drinking water, right? All of that is very important. And that data will be continuously sent. But it's not going to be all analyzed by the farmer. It will be sent up to, CA, for example, or other service providers who will analyze that data to try to identify ways for the farmer to improve. The farmer is not going to be the entire brains of this. It's not going to be a localized event. It's going to be carried, transported to different cloud-based services that are then going to turn around and send that amalgamated and analyzed data back down to the farmer. Right? In other areas, we're going to see, for the transportation industry, of course, there's going to be mapping of everything that moves through a particular site. And that data is going to have to be sent out of this site and be tracked in the cloud for headquarters levels and for analysis and instructions sent back down to the site. And that's going to be fairly regular data, and it's going to be fairly significant, and it's going to increase, and the analysis will go back and forth. But it's also going to be, and this is courtesy of Verizon, for example, they're looking at the ability to track medicines or time-sensitive items through an area by having their current wireless network track along every truck that's got monitoring capability, right? So they can say, is everything that's supposed to be at a certain temperature transported at the right temperature? Now, this particular one talks about medicines, but they're already doing it with tomatoes and agriculture and items, and tomatoes, cucumbers, anything that's a fast perishable, so they can pick it closer to full ripeness and get it on the customer's table faster. And by doing that, they're preventing you from having tomatoes that are not quite ripe and having to wait on them at your house, or overripe and disposed of. Right? So there's easy money to be made for the producers as well as the wholesalers throughout this entire infrastructure by having this data. So the modernization of Internet of Things is going to affect us in a lot of ways. We've already talked about FPGAs and the ability to adapt to changing requirements. Going forward here for a little bit, we're going to talk about more efficient packet technologies and better service controls. Right? The more efficient packet technologies would help in provisioning operation and the operational environment, where the better services control would be the human-machine interfaces, right? Being able to control that data much faster. Right? So let's take a look at some of the industry standard packet control mechanisms. Now, we've all been very used to talking about IP or carrier Ethernet VLANs. But there are other options out there as well. Right? One of the great things that the industry found about SONET was it was predictable, but it had a couple drawbacks. Every car was about the same size on that railway line, right? And everything was the same priority. Doesn't quite fit this IoT model where you're trying to figure out whether or not to stream Netflix to somebody, right, or pick up their data on their cattle for the day, right? So you kind of, right? I'm not quite sure who's going to figure out what's higher priority, but the kids are going to scream for the Netflix, that's for sure. But packet is like vehicles on a city road. Every packet is going to have its own size, schedule, and prioritization, right? And scheduling that traffic, that high priority traffic, can be confusing in the packet network if you don't have the ability to segment it easily, right? Somewhat analogous to the bottom picture, you know, you could create HOV lanes, virtual HOV lanes for certain time segments, or, you know, for certain time segments to say, you know what, whenever I got something to go down the HOV lane, it gets priority because it's supposed to get there fast, whether that be for first responders, high efficiency traffic, safety buffer for congestions for motorcycles. And we can turn that around for our applications to say, for first responders, in other words, traffic that's meant for 911 services or anything such as that, fire, etc. Right? Traffic that people have paid, for, you know, that they want to have delivered as quick as possible, right? Or traffic that you don't want to have, you want to have low jitter, like TDM traffic. They want the safety buffer around it, right? And you want to be able to restrict larger vehicles to certain lanes so that you're not overwhelming, you know, certain types of traffic by other types of traffic. Right? MPLS-TP was really derived for that purpose. It was specified in the mid-2000s, started by Alcatel and then Alcatel-Lucent as a way to maintain the SONET-like provisioning models. In other words, I can see where things are going. I know what's happening. I can isolate certain traffics. I can define what's going to happen in the network, right? But still use all the efficiency of, you know, packet and IP-like traffic. So it has a connection type, so it's connection oriented between locations, right? It has 50 millisecond protection switch times on a per service level or on a per path level, right? So it can do both. It's not all just ring-based switch protection where everything gets protected, you know, a certain way, or only one type of protection. With MPLS-TP, you can have multiple layers of protection. All the OANM is, you know, is in-band for the fault, but you provision from the NMS or from SDN, thus eliminating this flow control problem that exists in some IP networks where you're never quite sure where your data is at because it may have switched paths on you, or that you might have see a transmit down one side and receive down the other. Right? And this is done through a few simple elements, right? Similar to what MPLS was, but just slightly restructured. The pseudo wire is still there, but instead of an LSP, they call it a tunnel, with still full OANM capabilities. And for IoT, that provides you the ability to look at different infrastructures. So you can have enterprise in IoT, agriculture, transportation, or manufacturing, and you have different ways of picking up that traffic, right? And carrying it over, whether or not it be DWDM, but over MPLS-TP, transport that traffic either through to your local services within your rural telecom, or providing it to a national or a service provider that's in the cloud. It needs to be hosted services that the enterprise would subscribe to, or the farmer would subscribe to, saying, hey, I want to measure the moisture content of my grain on a daily basis, so I know exactly when it's going to be ready to harvest. That same efficiency can help out in wireless backhaul for both 4G and for upcoming for 5G, in that it provides good path control, right? Good jitter, good, and the best possible latency with predictable latency, because it provides a firm path with predictable latency through every device. So that's the services control part of it. The other part of it is, how do I operationalize that? Well, my brother still works for the farm, right? But he works for other farmers at this point, driving, and he rarely touches the steering wheel when he's doing his work, right? That tractor is, when he's planting or he's harvesting, he grabs a hold of whatever graphical interface that they have available to him, and with GPS, right, and a number of sensors on the tractor and on whatever equipment he's driving, right, he programs in where he wants to go and locks it in, and the computer takes control, and all he's there for is guidance at the end. And he sits back and reads books or watches a little TV. But the primary thing for him is, it's a graphical level interface. He can switch between types of tractors. It takes a little bit of time to familiarize himself with each different type. Not a big deal, but it's all graphical. And it's built around a certain level of control, right? And this level of graphical interface and control is built into every person under the age of 30 right now who's ever used an iPhone or a smartphone. They understand point and click, they understand apps, they understand how to do that. They don't understand CLIs very well, right? And by the way, my brother's turning 65 this year, and he still loves to do this stuff. So how do you get the next generation of efficient service control? Well, on the left-hand side, we have the typical CLI, where a lot of investment is made in remembering the instructions, or copying, pasting instructions, and trying to figure out how to change the instructions to get to where you want to go, get the objective done. So the first thing is you remember the instructions, and then you remember the objective. With a graphical-based system, whether that be at the node level or the network management level, you remember just the objective, right? If you want an L2 service, you click on the L2 service. You want to provision it, you hit the provision portion of it. It has drop-down menus. And this is common, whether or not be from, Tejas, which I pictured here, or other vendors, right? A graphical interface allows you to remember the objective. Right? And it is much more efficient at doing packet services when you can remember the objective. In fact, you can take it to the next step at a network level, having network level diagrams that show the network, not just the node. It can remember your service types, right? Both as the traffic comes in or goes out, or it can create tunnels and services. And this is what SDN controllers, orchestrators are looking to do for you, right? Whether it be an NMS or an SDN controller, they're looking to provide this level of functionality. They say, how do I move forward with all of this? Make it graphical, make it easy for people to learn. So that's the functions that we had, the 6 that we were going through when it started off with, right? How do I, leverage in technologies from the DWDM in the long haul? How do I take those industry advantages and that economic advantage that FPGAs have given to the industry and use those in my rural environment? How do I better tune my network for packet services and control those packet services, right, and manage those services going forward? and we summarized it like that. Right? So with all of that, I don't think I've seen any questions popped up here. So I would like to thank you for all of your time. Right? It's coming up at the end of the session. It's almost the end of the hour. So on behalf of Tejas Networks, I'd like to say thank you. Right? And I hope that we can talk to you in person someday. But again, I'd like to thank WTA for this excellent opportunity to, provide additional information to its members. And thank you very much, Kelly, for organizing it.